Okay, so the name of the topic is the integration by substitution, but I do want you to look at it in a broader sense, and that's why I started not with integration at all, but actually with change of variables, which is to begin with. It has an entirely separate value and interest, and so just because all throughout science, any kind of application of science, you change variables. Okay, and then still that topic has a relevance to, or rather has to affects the other two major subjects, and that's differentiation and integration. And so the first was integration, as you can see, and that's pretty much nothing but the chain rule, but you have to be very careful of how you do substitution. You have to be as explicit as possible if you do any kind of differentiation. The functions have to be very specifically written up so you can differentiate, because without the derivative, so where you get it. And then in that spirit, once we're done with this, we move to integration. And once again, starting with the simplest case, and that's where the substitution is linear, as it's almost invariably the case when we do change of units. Okay, so once again, it's almost always substitution is linear. So you rescale things, so it's inches and feet. Okay, and but then we will move to a more abstraction, and the topic is entirely of integration. But entirely matches the topic of differentiation, which is the chain rule. So it's entirely about the chain rule, and so I want to slightly go back and review the chain rule, because, well, what makes this topic so hard? It is because it relies on so much. It relies on understanding compositions, and even if you have compositions, then the chain rule. So in my experience, the chain rule is, understanding composition is really what stands in the way. And this is more convoluted. If you just look at this formula, which is simply the simplest one so far, from the simpler version of it, it is quite convoluted in comparison to even the chain rule. Okay, so this is how it works out with linear substitutions, but if we go on to do with substitutions that are not linear, it's still about the chain rule. So the chain rule review. Okay, so in the compositions. Okay, so it is an operation on functions to begin with, but very does not fit into the list of operations that we use more casual: addition, subtraction, multiplication, division. Those operations are really about numbers, and because they apply to numbers, that's why we can do that with functions too. But compositions apply only to functions. So once again, either you think in terms of functions, or you think in terms of variables. And in this particular case, thinking in terms of variables versus functions is better. So in other words, you have a variable from say just the way we did it just recently. So there's a functional relation between variables. Okay, and then say z. Okay, that's the composition. So for variable x to variable y to variable z, and then there are then two functions, which might be unnamed. Now remember, when we talk about compositions, you certainly have you remember those. There are some parentheses and so on. But this is all you can do. So for example, let's make it specific: x to y, and y is equal to, say, x squared minus 1. Okay, and then from y, the second consecutive step. That's the special thing about compositions, that computation is consecutive. And then we express z in terms of y as well. So z is equal to, say, ez. Okay, well, that's all. As you can see, there are three variables, and then two functions connecting them, and there is really no there is really no need for names of functions if we have explicit formulas. Okay, so then there are two separate situations. One is this. So this, if we concentrate on one function at a time, then y depends on x. So in this particular case, then x is independent and y dependent. If you look at this box, as you can see, that indeed is true. So y explicitly depends. Y depends on x. Okay, and then the other one is this. It doesn't really matter what y is. Let me make that clear. Y is really not part of the story here. So I'll just put a y here. Y, like this. Okay. So so it's the same y, but okay, like this. So the second arrow, and the arrows stand for functions. And then y is the independent variable, z is the dependent variable. Okay. And then so as you can see, why do we call it substitution? That's why we call it integration by substitution, because this substitution. So if you wanna, yeah.
Did you mean to write z equals e to the y?
Yeah, that's right. Thank you. Yeah. Okay. So messed up here. Okay, like this. Okay, so the relation is pairwise, relation between the three variables, but really two pairs of variables, but there are three. So we go from x to y, and then from y to z. So if we have covered these transition, then there is the third, this one, okay, and that is the composition. So either you can get from x to y from x to z directly, or you take this path from first go to y. The result should be the same. Okay, and then you substitute. So substitute in order to find the composition. Okay, substitute, and then I have z is equal to e to the u. Replace. Well, I'm sorry, I did it again, didn't I? It's y. It's y. Okay, and then I substitute e x squared minus 1. Okay. So that's a substitution. That's why it's called differentiation. It's not called differentiation by substitution, only integration by substitution, but it is about the same story. It's about compositions, and they're actually carried out compositions by substitution. It is more often the challenge is to decompose rather than to compose. That's the so we have the two functions have been composed here. Okay, decomposition, as you remember, is the bigger challenge, because you have to take something apart rather than the substitution is very direct. You plug it in and you're done. Okay, it still takes some skill, because substituting number is easier than substituting a function, but it's still the same story. So let me do maybe this one more time. So y is equal to still x squared minus 1, but suppose z is equal to, say, sine y divided by 1 minus y. Okay, so to make the point that the substitution, you might have to do it more than once. So as many times y appears, that as many times you have to do the substitution. So then if I want to carry out the composition, I plug it in. I have sine x squared minus 1. Notice how parentheses appear suddenly. So sine y doesn't require parentheses, but here you definitely need. Imagine that if I omit these parentheses, you can see what happens. Trouble. Same in the denominator. If I just write 1 minus x squared minus 1, trouble. So parentheses. So when you substitution, you can just draw parentheses first and then replace it. Put that thing here. Okay, so so that is the composition, but the decomposition is actually what we encounter more frequently. So the chain rule allows us, as well as differentiation by substitution, the chain rule allows us to differentiate functions that are not subject to other functions. So then we have to find such a decomposition in order for the chain rule to be applicable. So then I have to decompose. So this is how we compose, and this is how we decompose. Say so z is equal to 1 over square root of x squared minus 1. So you have to. It takes a bit of practice, but seeing compositions are very important, and so you just specify. Well, it is in a way it is also substitution. So even though we're doing decomposition, but actually the substitution, except we're replacing over here we replace something simple such as y with something more complex such as x squared minus 1. And now we do the opposite. As soon as we decide what our substitution is, we replace what should be our substitution. Y equal x squared minus 1 would be a good choice. So as you can see, we're still doing substitution, except in the things become simpler. So once again, substitute. So what then z is equal to 1 over square root of y. Okay. So and then my decomposition is this. This is the decomposition. And whether you're doing integration or differentiation of a function like that, that is the key. So either you do differentiation, you need to know what the function on the inside or the chain rule. Okay, so these are the two functions to be differentiated. Okay, so let me just do the chain rule as an example here. So I differentiate these two. So I do, as you can see, they're written very explicitly, so you know which one is the variable, independent, which one is an independent variable, two separate situations. And so I do dz dy here, dz dy, and so it will be, so how do we differentiate this one?
The left one?
What?
The left one, you said?
What was the word?
Z.
The left one, yeah.
Over.
Yeah, so, yeah, the z. So, what formula we apply? Roots? What do we do with roots?
Turn them power formula.
Into a power function, and then use the power formula. Okay, so just checking that you remember, but the answer is 1 over 2 squared of y. So let's skip that part. And then we do the same with the other one. So dy dx is 2x, and these are the two derivatives that are to be multiplied according to the chain rule. Okay, so this is then by the chain rule dz dx. So the original function. If we are to answer the question about the derivative of the original function, that decomposition is just a way to get there. And so we decompose the function. We have two functions. Each of them is fairly easy. We differentiate them. Now we just multiply. So this is as dz dy times dy dx. And they are exactly in that order, 1 over 2 squared of y times 2x, right? And so which gives me x over square root of y, which is not the answer, because what? Why isn't this the answer?
You have to substitute in the y.
Right, but can you, that's right, that's how you solve the problem, but why is it not, well, why do you substitute?
You have to get rid of the x on the top.
Of y.
You
So,
need just one variable.
but one variable is specifically which one, it is x. So the original problem is in the circle, so that we know that there is no y. Well, that's actually, there is no y. There is no y to begin with. The y was introduced, so we introduce y. Okay, so you can think about it as if your boss gave you a problem to be solved that in the circle, and then you sit down and start solving it and you introduce y. But then you have to give the answer in the same form the problem was posed. So z is a function of x, so there is no y. So, well, then you have to get rid of it, and it's called back substitution. all of this will reappear as we start integration. So back substitution is our choice of y, is what made it happen. So it will be x divided by square root of x squared minus 1. Okay? So the chain rule, one of the harder parts of the course to begin with, and then we are combining this complexity of two derivatives and understanding compositions and decompositions, and we combine it with integration, which is hard enough. So that's why this very topic is at the very end, and it represents a challenge, and it spills over a lot into calculus 2 as a matter of fact. So any of you taking calculus 2 next semester? Okay, so I might be teaching one of those sections. Okay, so that's the answer. So let me circle that too. Okay, dz dx. So if the original was circled, this is what you submit to your boss. So whether you submit what's in the middle is up to your boss. Maybe he wants to check your solution, but generally, if he trusts you, you'll just take the answer and move on with it. Okay, so all right. So and now you can imagine what happens if we want to do differentiation. I'm sorry, integration now. So the decomposition is still needed. Introducing a new variable still necessary, but and then things become complicated because this works every time. So that's the good news about the chain rule with all its complexity. This works every time. So you have a composition, you decompose, differentiate, multiply derivatives, you're done. So like this, it works every time. So there's no doubt about it. Not so with integration by substitution. The way we have what we have seen so far actually worked out every time, but that's only because the substitution was linear. This is our y. This is our, not this one. This is our y over here. That was our y, and as long as if it is if it is linear, then once again it works out every single time, and that's why we have a whole formula that proves that. This is the formula, and once again I can say works every time. But once again, the substitution, this is mx plus b, so you already can compare to the chain rule that we just saw, that would take any function that you can imagine, say such as x squared minus 1, that was my function on the inside, and the new variable, and it works out. And the equivalent statement for the integration only works when your function is linear. Okay, so when the function is linear, as you can see, it will work every time. So what to do if the substitution is not linear? Well, the answer is pray, because it's quite likely that you encounter a function that it cannot be integrated. Of course, all the tests and homework are designed in such a way the problem has a solution. Okay, so not to worry about it, but also not to forget that it is quite possible that no substitution will work. So as an example, so to make that point, so integrate a very simple function, say let's see, ex squared. Okay, so well, first of all, let's differentiate quickly as one more as a side note. We differentiate just to see how that it works out. There is no problem. So so z is equal to e to x squared. I introduce new variable. Y is equal to x squared. I differentiate these two. Not these two, but rather first of all I do the substitution, right? So this is introduce new variable, substitute, which means that I express my old variable z in terms of the new variable y, which is what? E to the y. So these are the two functions that this is the decomposition. I differentiate the two. dz dy is e to the y. dy dx is 2x. Okay, So everything is fine. The chain rule then produces the answer by multiplication and back substitution. So dz dx then is equal to the product of these, e to the y to the 2 to the x, and or ex squared 2x. Okay? Works out. So once again, there's a side note, a big one, but it is just one more time of the chain rule probably is a good idea anyway. And then they integrate, and the answer is well, this cannot be integrated. So what we're supposed to find a function, say f capital of x, such that what integration means, f prime of x is equal to ex squared. Okay, so first of all, we still see the composition. So if we were to try to do anything about it, then this will be still my y, probably. Okay, but it's okay, great. But we know that if we differentiate a composition, we know that should come from a bit of experience by now. Is that there's a coefficient. That thing is a big deal. Every time you apply the chain rule, you multiply two derivatives, and the derivative of the function inside will be visible as a coefficient. So 2x is a coefficient. In the previous example, also 2x just by coincidence, because our variable was x squared minus 1. But that coefficient will always appear, and the result of the chain rule is always a product. That's what chain rule is. It is the product of two derivatives. So there will be always a product of two things. So then we look at what we've got, this function over here, and we realize that this function, it does not have an extra term, a product of two things. It has only one thing, and which means that it is probably, this is not a product of two functions unless it's a constant. Unless one of them is constant, but then we are talking about linear substitution. Okay, so once again, if you try to differentiate any kind of function, and the x squared is the function on the inside, there will be coefficient 2x somewhere, and this one does not have it. So the lesson is fully visible from from the actual differentiation. So this one does not have an antiderivative, ex squared, not in the elementary sense, not any of the familiar functions, nor a combination of familiar functions. Okay, and then if we look back at our differentiation, we realize that the function that we have over here is, though more complicated, is in fact can be integrated, and it has been integrated. So ex squared is hard, ex squared times 2x is not. Why? Well, you tell me. So integral ex squared 2x dx is equal to no, look at the green. Look at the green. The function that I wrote here, it's the same as here. It is this one. It's the same function. We already know what we need to differentiate to get this function. What? Ex squared. This is the answer. Well, plus c. But otherwise, that's the answer. So if we have differentiated at some point, found the answer, we can always reverse it and call it anti-differentiation. That's what I just did. And as you can see, if differentiation works, then if we know the answer, we can find the question. That's what has happened. if it is the answer. But unfortunately, such as x squared, there is no question for it. There is no a function that you differentiate, you get this function, ex squared. So then every time then we do something like this, then you can see to integrate with the chain rule reversed. So this is chain rule reversed. What do we every time we have? We have two parts to see. This one and that one. This one is a composition. And this one, what's the meaning of the second one? It is the derivative of the function on the inside. So let's say second function. When we decompose ex squared, then the x squared is the function on the inside, or a new variable on the inside. And then we got to have its derivative standing there to be used in order to reverse the chain rule. So if you reverse the chain rule is the product. Therefore, it will have to have always two terms. So when there is no third term, you probably are stuck with certainly the decomposition doesn't work. So with just a few exceptions, you're not gonna integrate it. When you see two terms, then a product of two things, then there is a good chance that you can carry it out. Well, here's an example. So once again, how about I do sine x squared 2x dx? Now let me put cosine here, just keep it simple. So cosine x squared 2x dx. Can you guess the answer? Thinking backwards, applying the reverse chain rule, we do have that two parts, as I indicated. This is one part, the composition, and the derivative of 2x is right here. So what's the answer? Sine x squared, yes. Okay, so as you can see, it is almost a guessing game. So that certainly is not a good idea, but it is a starting point. Then we'll formalize it. Let me do one more. Sine x squared 2x dx is negative cosine x squared plus c. Okay, so you can certainly have a lot of similar ones. Let me. How about a square root of x squared plus 1 2x dx. So this sign, the function on the inside is not x squared anymore. It's x squared plus 1. So x squared plus 1 is our variable, say y or u, as it is frequently called, and then this is du dx. So my u is x squared plus 1, du dx is 2x. Okay, so just like in the chain rule, so once again, two parts, the composition with the square root here, and the derivative of u is right there as the second term. So it should work once again. So what do we get? The power, so it's 1/2. You got to integrate. What's the integral of square root of u? So you got to put here something. What's the integral of square root of u du? No. You don't differentiate. So you integrate there. Remember, it is still power formula. The power goes up when you integrate. So it is, in fact, what is it? U 3/2 over 3/2. Okay, so that's what we're going to use, and then we just need to substitute u. So I'll have then x squared plus 1 3/2 over 3/2 plus c. Okay. So that is the thing that we that's how it works out, and this is the way to formalize this kind of informal, the very haphazard way of doing things is right here. It is introduce the new variable explicitly, as I did over here. Okay, so this is supposed to happen, and then evaluate the integral with respect to that variable. Okay, so that way you don't have to guess, even though you might still have to face difficulty with that integral, that integral, but it has been simplified. Look at it. The integral on left, the original integral here, well, the original integral here, and compare it to the one in green there. It is simpler, and so in this particular case, all we needed to do was to find that formula for, it is a power formula for integration. Okay, so let me do it one more time in a more explicit way, the same problem as this. So once again, so what do we do? So my integral is the same, square root of x squared plus 1 2x dx. Okay, so what do? I introduce a new variable, so introduce. It is often called u for whatever reason, and sometimes it's even called u substitution, just in a name for informal. So anyway, you decompose. So introduce new variable, not in a random way. It always comes from the same place. You've got to be substitution. So you pick a composition, but you first have to point out where the composition is. This is the composition. So you ignore this part and hope that it will work out, and then look at the composition, decompose it into two functions or three variables. So one variable is x, and the other variable will be y, which is this, or u. Okay, so my u is x squared plus 1. Okay, and then I will need its derivative. So it's a weird thing that we actually need derivatives rather than for integration we need derivatives. So the integral is 2x, and then now we're stepping into something that really doesn't have a lot of an explanation in this course, other than that it works. And so what I mean is what to do about dx. So that's a question that we need to answer. What to do with dx. Why is it a problem to begin with? Because when we start doing substitution, so these two things will be substituted into my integral. And what do I get? I get my integral is square root of u 2x dx. Well, let's one at a time, and then the problem becomes what to do about 2x dx. And indeed, it is. We see it right here. What it is. 2x dx is du. Okay, so that converts the integral from 1 with respect to x to 1 with respect to u, which is what we want. Certainly, it does not leave me comfortable or satisfied when we make that such a replacement, because after all, we didn't really never explain how dx, what's the role of dx in the integral. Best we said just it's like parentheses. It's like parentheses. You have integral on one side and dx on the other side. So and what's inside is the function to be integrated. So that's the common understanding of this notation for the integral. And then we suddenly, at this point, for this particular type of method, we decide that, well, actually dx has a meaning, and it turns out that it comes from over there, from here. That's the meaning of what dx is. It actually is not only that, we also treat dx as a du dx as a fraction. So that's the most uncomfortable thing that, mathematically speaking, that we have to face. Is this a fraction? We know that it is not. I mean, it is derivative. Derivative is the limit of a fraction, but it's not a fraction. So you certainly don't try to flip them up or cancel or do any kind of a common denominator or any other algebra with this. It's not a fraction. It just was written this way by Leibniz, who was one of the creators of calculus, and so he just did it. He didn't think in terms of limits, not exactly. So he just a way to sort of remember the way I always thought of it, as it's just a way to remember where it comes from. It comes from a difference quotient, which is a quotient, and it comes from delta u over delta x. That is a fraction. And then you take its limit, and then it stops being a fraction. It is a number. So I certainly at some point give some explanation of this. There's an explanation. But at this point, we just use it as if because it simply works. So it works. We can verify it. Well, let's finish this problem and confirm that it indeed works. Well, we already know that it works, but let's carry out this method all the way through. So we treat du dx as a fraction. We understand that, which means that du is equal to, or rather, dx is equal to du. What did I do here? Du is 2x dx. Okay, so from over here. Okay, and then we can have converted our integral to u, 1 for u, which is simpler than the original. So that's a success. We now integrate with respect to u. We have 3 halves u 3 half. Sorry, u 3 halves divided by 3 halves plus c. So integration with respect to u. Period. Back substitution. I have my x squared plus 1, and this gives me the whole method right here in on this page. So beginning from the very beginning to the very end. So the beginning is here and the end is there. In the middle, this funny business in the middle of treating derivatives as fractions. They also thought of these fractions as like infinitely small, two infinitely small quantities divided by each other, whatever infinitely small quantity is. So they didn't really figure it out. And then later, only in the 19th century, they finally came up with the idea of limits, and they did it very carefully. Okay, so the explanation is actually not too hard, but it a bit will take us off course, I'm afraid. Well, let me just make one little picture. So where is the fraction? This is the fraction. The fraction actually is it comes from linear approximation. Where do you see the how can you think of the derivative as a fraction? And that is, it comes from the linear approximation, because so f prime of a is this. No, I think I'll do it next time. Yeah, it just takes some setting up some time. So the homework has been assigned, but it's not going to be any of this yet. It's still about just Riemann integrals. Okay, so tomorrow, we'll see tomorrow.